Welcome back, everybody. So we'll have our final two talks here. Our first one is lattice-based timed cryptography by Russell Lai and Giulio Malavolta. And Giulio will be giving the talk.
Okay. Can everybody hear me fine? Okay. So yeah, as Chris mentioned, this is a joint work with Russell, and so we're going to talk about time cryptography. So let me start by telling you what time cryptography is. So in my view, time cryptography captures all of the cryptographic primitives whose security properties are required to hold only for a predetermined amount of time. And some primitives that you may have heard that belongs to this class are time lock puzzles, proofs of sequential works, and verifiable delay functions. And let me say that I have an application slide. So here is a bunch of applications that are implied by time cryptography. But perhaps you can look at the paper, like essentially any paper that has been written on such primitives has a list of these applications. But maybe the sort of modern take on this is that time cryptography is actually useful and used in blockchain companies. So these are two examples of two blockchains that actually implement and run instances of time cryptography. And so we're not allowed to say that these things are practical applications. Okay. So before I get to the point of the talk, I want to make a slight, maybe slight philosophical detour and talk a little bit about the difference between the kind of computational assumptions that you would get when you do maybe more traditional cryptographic primitives versus the ones that we consider in time cryptography. So traditional cryptographic primitives such as one-way function, there you require a problem to be hard, let's say against all polynomial time attackers. And the picture looks like this. And in particular, essentially all of the sort of more traditional computational assumptions, one thing they have in common is that they all imply a separation between the complexity classes P and NP. It's probably, you know this better than me. Okay. But if you look at the sort of time version of this, we require problems to be not hard for all polynomial size attackers, but just for the ones which have depth bounded by t, where t is some parameters. And depth by that here, I mean just in the sense of the circuit representation of the attacker. So we only require security against a sort of very shallow circuit, although we don't actually impose any restriction on the width of the circuit, which models the fact that the attacker is allowed to have as much parallel computation as he wants, and we still require the primitives to be secure. Again, one thing that all these primitives they have in common is that they imply a separation of these two classes, where NC is for those of you who don't know, is the class of circuits of logarithmic size. Of logarithmic depth. And so now you can see for yourself that these are really just two different classes of primitives. In particular, we could imagine living in a world where NC is equal to P, but one-way functions exist. So this already tells you, I mean, I'm not saying it's likely, but it's a possibility. So this in particular tells you that when we think about such time cryptography, it's unlikely that we will be able to use traditional assumptions such as VDH or LW. Okay, so with that out of the way, let me tell you what is known in terms of, or what is conjectured to be sequential in the land of time cryptography. So here I have a graph where on the y-axis I put structure. Structure is not really a well-defined term, but it essentially captures how many applications, how useful is this sequential function. And on the x-axis is real world versus theory world, which tells you how efficient versus inefficient the applications that we can build are, okay? And of course, the best is to be in this top left corner. And in fact, in this top left corner, we have the repeated squaring assumption, which essentially says that taking repeated squares in groups of unknown order is a inherently sequential operation. So it's an operation that we don't know how to parallelize. And we conjecture that we cannot parallelize. And this is great. This is very structured. We can construct a lot of things out of it. And it's also very efficient. Like all these applications are pretty practical that we can construct from it. The next thing that we have is random oracles. Now, random oracles are great. They are super efficient. It's just a hash function. And the great thing about random oracles is that we can actually prove that they are sequential in the random oracle model, of course, but we can prove that they are sequential. But one drawback of random oracles is that they are, in a sense, maximally unstructured. So there is a random function. There is absolutely no structure in the function. And this is reflected by the fact that many of the applications that we can construct from repeated squaring, we cannot construct from random oracles by themselves. Okay. Now, as we shift towards the right of this graph, we have the isogeny shortcut problem, which is fairly structured. But is considerably less efficient than it's causing repeated squaring, which essentially says that jumping from one isogenies to another is an inherently sequential operation, and I would refer you to the paper for a more formal description. And finally, on the sort of very, very right side of this graph, we have the so-called universal constructions, which use very heavy cryptographic machinery, such as obfuscation or fully homomorphic encryptions. Those are like beautiful construction paradigms, but unfortunately, the applications that we get, they are nowhere close to be practical, at least in the time cryptography world. Okay, so and now the question that we ask is what happens when we consider quantum computing? So enter quantum computing. Here it is. The first thing that we notice is that the repeated squaring assumption immediately disappears from this graph just by virtue of not being sequential at all, because you can just use Shor's algorithm to compute the order of the group, and that's it. So it's obviously not sequential. And the isogeny shortcut problem also becomes a little bit less interesting because the problem itself does not appear to be affected by Shor's algorithm, but the applications that you build on top of it require things like the discrete logarithms to be hard. Not all of them, but some. Okay, so now obviously this might feel a bit unsatisfactory. In particular, we are left with a hole on this top left corner, and the question that we ask in this work is whether we can fill that gap. And in particular, we ask, can we construct efficient post-quantum time cryptographic schemes? So now let me give you a little bit of a summary of our results, which will also serve as the roadmap for my talk. What we're going to see today is a new candidate, lattice-based sequential function. Again, lattice-based in quote. You'll see why I call it lattice-based. We provide some evidence of sequentiality. Again, it's very hard to prove anything in this domain against traditional assumptions. So this sort of, in a sense, justified the need to come up with a new sequentiality assumption. So the best we can do to gain confidence is to give some evidence. We propose some cryptanalysis and some initial attempts to break the sequentiality of our function. And then we see why this function is useful. We present a very simple proof of sequential work that have better soundness guarantees than existing protocols. You'll see here the protocol sketch and the analysis, and a sketch of the analysis. And finally, I'm just going to conclude with some open problems that I think they are particularly interesting and I'm very excited about. And I hope you share my excitement and decide to work on it. Okay, so without further ado, I'll present you our new sequential function. So the input of this function is a uniformly sampled matrix A and a uniformly sampled vector. And the function proceeds as follows. First, it computes the binary decomposition of the input. And then it computes this linear function, A times U mod Q. Okay, this is the function. And the t-fold repetition of this function is defined in a very natural way by just essentially feeding the output of the function again as an input of itself. And you can make the parameters match so that this operation is well defined. Okay. Now, yeah, if you alternatively, another way to sort of rewrite the function is to do this, but this is literally what I said before. But an equivalent way to check this relation is to find the binary U that is a pre-image of these x and y, which are the input and the output of the function, with respect to this matrix. And now the point, of course, U is binary, but in particular is short. And this already bears a lot of similarities with the SIS problem, and that's where the connection with lattices comes. Okay, so and as a bonus, you may have noticed that our function is essentially just a bunch of linear layers alternated by nonlinear operations. So yeah, so if you work on these things, you can write in your grants that your research has connection with machine learning. So yeah, it's a win-win. Good. Good. Okay, so now I told you the function. What is the assumption? The assumption is very natural. It says that for a uniformly sampled matrix A and input X, the t-fold recursive application is sequential, so we cannot parallelize it. And in other words, it takes parallel time t to find a binary U that is a pre-image of this vector. This is just specified by the instance x and the output y, and it's otherwise 0 everywhere. With respect to this block diagonal matrix, and the sort of number of blocks will depend on your time parameter t. Okay, I just rewrote the same thing, except in this more algebraic language. But this is actually useful because I'm going to need a slightly relaxed version of this assumption, where the only thing that I'm going to do is that instead of forcing U to be binary, I'll just require U to be short for some appropriately defined metric. Okay? And the assumption is now the same, except that we relax the condition of binariness to the condition of shortness. Excellent. Now, why do we believe that this function is sequential? Well, the function, we can prove some stuff. I mean, of course, we cannot prove that this function is sequential, as I said, based on traditional assumptions. But we can prove that this is collision resistant as a hash function. And this is just a very simple reduction to the SIS problem with respect to the matrix A. We can prove that this function is uniformity preserving, which is essentially says that if you look at just the marginal of each function step is uniform, provided that the input was uniformly sampled. Again, not very difficult to prove. And in the paper, we have other sort of more heuristic arguments along with some cryptanalysis. So our philosophy to prove sequentiality is to sort of show that this function shares as many properties as possible with random oracles. And the reason is that random oracles, we can actually prove that they are sequential. So the sort of closer they are, the more confident we can be about the sequentiality of the function. Okay, so that's it. Yeah, that's what I just said. So let me just jump to the application. The application is a proof of sequential work. So let me quickly define what that is. Proof of sequential work is an interactive protocol between the prover and the verifier. The verifier samples an instance AX uniformly, and the prover returns an output. And they are allowed to interact a little bit, and then at the end of the protocol, the verifier returns a bit, meaning that is convinced or not. And we require two properties. So the first property to make the protocol non-trivial is succinctness, and we want that the verifier work is much smaller than having to recompute this function. So we want that the verifier total work is sort of logarithmic in the time parameter t. And the next property is that of soundness, which essentially says that no prover of depth t can pass the verification except, of depth sublinear in t can pass the verification except with negligible probability. Well, I didn't write completeness here, but completeness says that the prover of time t can always pass, which is the case. Excellent. So this is just what we want to achieve. And the main property that we're going to use is this sort of self-symmetric property of our block diagonal matrix. So if I denote by A capital T, the matrix with T many blocks in the diagonal, I can actually equivalently rewrite this matrix as as having like two little copies of itself on the top left and bottom right corner, except that these two little copies have roughly half of the dimensions of A. Okay, so this is really an equality, and this is the property that sort of will enable fast verification of our proof of sequential work, which I'm going to describe next. Okay, very, very simple observation. So let me describe the protocol. So the first thing that the prover does is sends the middle value of the computation. So the sort of at half of the computation, whatever was fed to the function at time t divided by 2, we call this value u little t. It just sends it in the plane to the verifier. The verifier checks that ut is small, which is trivial to do. And now the new relation is essentially this. So note that we have roughly half the dimension of this matrix A, but now we have two columns of this matrix. So namely, we have to check two relations of half the size. But at this point, we have not really saved anything because we've just broken down the relation in two. Right? I mean, the matrix is a little bit smaller, but that so far we haven't saved any work from the verifier side. But that's what we are going to do next. So the verifier will sample a small integer r, and we'll send it to the prover. And this defines the new relation, which is defined by essentially taking the linear combination of these two columns based on the r that the verifier has sent. And it's important that r is small so that this doesn't blow up the norm of the witness too much. But this can be done. And note that the verifier can efficiently compute this locally because he knows ut, which was sent previously by the prover, and he knows little r that is sampled on its own. And now we have a relation that looks exactly like the previous one, except of half of the dimension. So we can recurse. And if we do it sufficiently many times, and we set the parameters judiciously, we get that verifier runtime is indeed logarithmic in t. Okay, and so that's literally it. I mean, I've been a little bit sloppy with the kind of arithmetic and with the exact rings that we're using. We cannot use the integers, but you know, I'll defer your curiosity to the paper for that. But literally, this is the protocol. Okay. Now, there is actually a standard way to prove soundness for this kind of protocol, namely to prove that they satisfy KKK, or in this case, just 2-to-2 special soundness, which essentially says that given a binary transcript, a binary tree of accepting transcript, one can, just by looking at this transcript, recover a valid witness for the relation that we were trying to prove. And this can be shown for our protocol as well, if we sample challenges from the appropriate set, which is not something I've been telling you how to do, but again, technically it's a subtractive set, but you can refer to the paper for this kind of details. So we have this, and the next thing that we need to do is that we need to take a cheating prover and describe an extractor that allows us to obtain such a binary tree of transcript. Unfortunately for us, this problem is very well studied. A recent work of Atem and Fair shows that there exists an extractor for the parallel repeated version of the protocol. And very crucially for us, this extractor is depth preserving in the sense that the runtime of the extractor is just a little bit deeper than the runtime of the original prover. It's allowed to do much more parallel computation, but it doesn't add a lot of that. Okay. Now, this is somewhat interesting because the authors there did not care at all about this property, but it somehow emerges for free from their analysis. So yeah, good for us. Anyway, and if we have such an extractor, it means that we can extract a valid transcript in time sublinear in T, and this is just a contradiction to our to the sequentiality assumption that we postulated before. Great. So that's so much for the intuition, and I'm sort of going to conclude the talk by stating some open problems that I think they're particularly exciting, at least from my perspective, and I hope this will motivate you to think about these kind of problems. So the first problem is to do an efficient lattice-based verifiable delay function. So now I've shown you a proof of sequential work. And the difference is that verifiable delay functions, they have an additional requirement, which is output uniqueness, namely that you cannot sort of cheat and pretend that an output was not the correct output of the computation. This does not contradict sequentiality, right? It's just you're producing a different output. And unfortunately, our protocol does not satisfy that property. And there's actually a pretty easy attack if you try to prove it. So there are many ways in which you could attack this problem. For instance, one could try to design like the best succinct argument to prove that the relation that I showed you before with the binariness constraint is satisfied. And yeah, one candidate construction that we proposed was presented earlier in this conference from Valerio's talk. If you haven't seen it, you can watch the recording. But we haven't implemented it, and I think the sort of to declare victory, one should really give us an implementation of this, or something we can conceivably and decisively, you know, run on our computers, and just do everything from lattices. That'd be extremely helpful. Good. Another thing that of course is very interesting is whether we can, you know, get more evidence of sequentiality. Can we gain confidence in our candidate? Is there something we can prove that increases our confidence? One can prove, one can approach this from many angles, like complexity angles. I think it's very interesting. Can we construct more applications on top of these functions? There's many cryptographic primitives in the time cryptography landscape. Can we take any of them and construct them using the extra structure that this sequential function is giving us? Finally, there is a very interesting theoretical problem, which is about the post-quantum security of our protocol. Currently, what we can prove is that the protocol is secure against even a quantum adversary, but with a classical advice. Whereas it would be extremely interesting if you could upgrade our proof to sort of true post-quantum security, which it requires an adversary to have a quantum advice. And we don't know how to do it. And the sort of technical challenge lies in the depth preserving extractor, which I think is like probably a question which is interesting on its own right. Yeah. With that being said, I'd like to conclude, and I'm happy to take questions.
Thank you very much. We have a minute or two for a question. I guess I have one. I'm going to ask you one quickly. What are some of beyond VDFs? Are there more advanced timed objects what would be your favorite one to get?
Oh yeah, so definitely my favorite would be time lock puzzle, if we could time lock puzzles. So which is like the timed equivalent of encryption. Mm-hmm. Yeah, it would be extremely interesting if one can prove a construction. Again, we have like sort of generic construction using very generic machinery, but if one can do something that we can actually implement, it would be really great.
All right, let's thank Giulio again. We'll get your slides up. Great. Okay. Our final talk of the session is revisiting security estimation for LW with hints from a geometric perspective. The work is by Dana Dockman-Saled, Huijing Gong, Tom Hansen, and Hunter Kippen. And Hunter will give the talk.
All right. Thank you so much for the introduction. You know, I was going to originally give a joke about saving the best for last, but I obviously got nowhere close to winning best paper, and Giulio's talk before was really excellent. So can't really do that. But you know, this is a little bit, it might be a little long, so I'm going to just try and get into it. But I've tried to make this talk very accessible, especially since you're all probably very tired. at the moment, as am I. Okay, so I want to say the motivation for this talk really is about the fact that our community has done incredibly well. Our advanced cryptography is really starting to see quite widespread deployment. This includes, our secure messaging systems, multi-party computation frameworks, our post-quantum protocols, and unfortunately also cryptocurrency. But and the thing that these things all have in common is that they invite increased complexity. And with this amount of complexity, we also end up with somewhat of a larger attack surface. There are more attacks that are applicable when you actually deploy these schemes in practice. And when it comes to actually deploying these things, we have to really consider concrete risks of these deployments. So that might include the exact computational costs that are involved in particular implementations or deployments, the mathematical hardness of the problems involved, or possibly, depending on the use case, possibly security degradation over time. If you have something that's very long-lived, there could be leakage either from just it depends on the framework or the exact model that you're going for, but you can end up with this thing. And if you're trying to, solve these problems with concrete risks, you can do one of two things usually. You can think about actually just straight up improving attacks for specific deployments. And there's a lot of literature on side channels that have spanned the corpus, and it's all of that is quite great. And also you could possibly create frameworks for tracking some of this security degradation automatically to aid in, setting policy and that sort of stuff. And so this work really focuses much more on the latter, and that's what we're trying to do here. And in particular, this is for lattice schemes, and more specifically LWE. But when we're talking about cryptanalysis of lattice crypto systems, I usually tend to think about it as like you have two different worlds that you can come at. Especially when you're talking about concrete, you can come at it from sort of the protocol or scheme design setting where you're saying, I have your crypto system, and then you think about what's the possible lowest cost attack for the system. So, whether it's a primal dual, whatever the exact attack will be best for your particular parameters. And then from that, you can say, okay, what are some, using the cost models or metrics for like memory accesses, computation, whatever you want to use, you can say, okay, based on that attack, I need 128 bits for key recovery, or you could come at it from, a specific implementation, right? So if you have your lattice scheme and you're observing the execution of a particular implementation or deployment, you can possibly figure out where some data might leak, and you can use some techniques like belief propagation or other probabilistic fusion tools to do that. And then you can say, okay, well, I need this many power traces or whatever for doing your key recovery. And so this work is considered with combining both of these things. So, say you actually have some amount of partial leakage. It's not quite enough for actually doing your key recovery, but you can, our goal here is to create a hybrid attack that introduces this information into your actual lattice reduction or other types of attacks. And so there was some prior work that created a framework for analyzing this exact impact of side information on security. And a little bit about this prior work. The idea really was to first categorize your side information into hints. They had to have a particular specific structure. And then with these hints, you could actually track the conditional distribution of the secret, your LWE secret over time, given these hints. And then you could estimate the remaining hardness in your instance. And these estimates were experimentally confirmed. And just as an aside, when we're talking about these hardness estimates, you'll see some graphs a little bit later. And so I don't want to blindside you by like the quantities. The hardness in this paper and in the prior work were measured in sort of BKZ beta or BIX, as it's called sometimes in literature, where the hardness is measured by the block size of the BKZ algorithm. BKZ runs is a blockwise lattice reduction algorithm, and the block size is exponential in the number of blocks that are involved, or the size of the sublattices that you solve. And there's various cost models for taking block size to actual bit security, and so we see that as an orthogonal problem to what we're doing here. And this required block size, at least for some rough estimates, solely depends on sort of the lattice dimension, your lattice volume, and then the length of your shortest vector in your lattice. And our framework manipulates really the first two quantities to make the hardness actually reduce. And so when we're talking exactly about hints, in the prior work, there were 4 types of hints that were introduced. There were perfect hints. These are for your high confidence leakage, exact leakage of either an inner product of your secrets and errors, or maybe an exact coordinate. You have modular hints. These could be things like NTT coefficients. Note though that this modulus doesn't have to exactly equal your lattice modulus. It can be whatever you want it to be. Or approximate hints. So this is for some kind of low confidence leakage. You have a pretty noisy measurement. And then there's short vector hints. I'm not going to exactly get into exactly what these are, but you can find short vectors in your lattice that might be defined by your scheme depending on how it's set up. But there's some limitations with these 4 hints. These hints actually can't really fully capture common leakage scenarios. There's some things with like Hamming weight, and if you get certain measurements where you're saying, I know my value is above 0, for example, or less than 0, but you're not exactly sure. And also possibly integrating, decryption failures, which is another mode of possibly leaking information when deploying chem schemes. And in the prior work, they did try to actually integrate decryption failures, and it was quite successful, but it required an approximation technique that I'll show a little bit later is not exactly 100% kosher. And so there's sort of a lack of rigorous guarantees on your estimate accuracy, in particular when the secret is not Gaussian, and many schemes for efficiency don't use Gaussian secrets. And the guarantees on sort of how much volume you would lose in your lattice were also only guaranteed for when the hint vectors were sort of primitive in your lattice. And so it's kind of hard to figure out exactly how you want to, like when we were starting this, it's not exactly clear, how we were trying to solve this, because we really want to add more hints and we want to add these guarantees, but it's not exactly, from the way it was set up, it's not exactly clear how we had to do this. And so really what we wanted to do, again, as I said, was we wanted to provide rigorous guarantees. And in particular, this guarantee that when you're actually performing these attacks and these reductions, your secret is always contained in your search space. So we treat this as an optimization problem, and we're making sure that like your secret is always contained in the search space of your optimization problem. And we want to support additional hint types, but trade off only a modest increase in complexity here. And from this, we actually were able to explore some new connections between linear programming and control theory. We actually, a lot of our new hint integration stuff comes from the linear programming algorithm, the ellipsoid method, which is quite cool. And this is a kind of a silly comparison table, but the point really is that we've changed sort of the way we integrate hints from tracking the conditional distributions to working more with geometry. And so we get to actually include 2 new additional hints based on this geometric work and provide these rigorous guarantees at the same time while maintaining compatibility with everything that came before. And so for the rest of the talk, I'm really just gonna go through the some basic concepts and then talk about our new hints and some applications at the very end. I'll try and get through this really quick. I'm only putting this slide up here because of notation. You all know what LW is at this point. You've seen plenty of talks that have defined it for you. I'm not going to bother. It's just that we're using row notation instead of column notation in our paper, and I just wanted to point that out because you could get it might get a little confusing otherwise. And as also as we know, LW instances can be embedded into the shortest vector problem, SVP. And attacks on SVP are usually carried out, obviously using SVP solvers, of which BKZ is one. And so that's your kind of normal attack flow. But the prior work introduced sort of an intermediate step that's a modified version of the bounded distance decoding problem called DBDD, or distorted bounded distance decoding. So it includes just a little bit of extra distributional information in your BDD instance. And what's nice about this is that this problem was self-reducible. And so you could, with every subsequent hint, you could reduce this DBDD instance to itself. Such instances were easier to solve, and then from there, complete your reduction to SVP and do the attack. And so in our work, we're particularly concerned at this point with modifying that first step, the initial reduction from LW to DBDD. And so, well, what is the DBDD problem? You're given two objects, a lattice and an ellipsoid. And when, but an ellipsoid itself, just really quick, is an affine transform. You can define it as an affine transformation of the unit ball or a particular set of points. This particular set of points is quite a useful metric, actually, because you can use it as a test for whether a point is inside or outside your ellipsoid. It's sort of a distorted Euclidean norm when you look at in this quadratic form. And you'll see why that's, there's some experiments that we show later that make use of this, and just wanted to point that out. And so the DBDD problem gives you this sort of promise that you're trying to find the unique lattice point contained in this ellipsoid. And in the prior work, this lattice, the original lattice basis was defined by Canon's embedding. And then, your secret point is defined as standard and, the standard way. And your ellipsoid represents, again, as I said a little bit earlier, the Gaussian distribution of your LW secret and error. And so that's where you sort of define your initial search space. You're saying, I know that the LW secret is within this, maybe first standard deviation of this Gaussian distribution with some constant probability. And it's also contained in the lattice defined by the Canon embedding. So the way you would reduce this DBDD problem finally to the unique shortest vector problem is you would homogenize first. So you would take your ellipsoid and stretch it in the direction of sort of the mean of the ellipsoid, so that you include plus or minus the secret. And then you perform a linear transformation such that you turn your ellipsoid into the unit ball. And what this will do is this will sparsify the actual lattice that you're doing, and then that you're using for the SVP, for solving SVP. And the larger the volume of this lattice is, the easier your problem is to solve. And you can do this by either shrinking sort of your initial ellipsoidal search space or sparsifying your initial lattice before doing this homogenization or isotropization. And integrating hints provides ways to do such. So when we're talking about in the prior work, all the randomness is contained in your lattice, right? Your LW system, your constraints. Every time you get a new instance, it's contained in your lattice. And what that means is that some geometric operations are actually kind of incompatible with this original formulation of the DBDD problem. Because, for example, imagine you're intersecting your DBDD instance with a half space, or combining two instances with the same secret. In particular, when you're doing this half space intersection, a lattice is an infinite object. You can't, suddenly cut it in half. You can't say, oh, I only have half the points of my space. It's not a lattice anymore. And so you can't really define a basis in the same way that you would for it. And that's quite unfortunate. So we need to change this embedding. And unfortunately, I don't have the time to get into the details of exactly how we create this new embedding. Please see the paper for that. But I want to impress kind of what we obtain from doing this. We get two new hints, what we call inequality and combined hints. The first set is we can support linear inequalities, and you can do certain things like say, oh, integrate decryption failures exactly, or maybe you say functions are greater than 0, or specific things about Hamming weight. Or if you have two sources of independent leakage, maybe you've done two different measurements and they're sort of at independent times, but they're on the same key, you can fuse those instances in an intelligent manner. And as I said, we support these two new hint types, and we can maintain compatibility with all prior hints as well. So what does that exactly mean when we want to say, I say we want to integrate these hints geometrically? Hints form a constraint system. So you can think of, since they're all linear, you can think about forming a convex body of all of the hints, like a big polytope of all the hints, and then just sort of but it's not clear exactly how you would describe that, and especially if you just use that as your new search space, that's not what the actual promise of the DBDD problem is. And so we need a slight relaxation of using this constraint system as it is. And so you could think maybe of constructing sort of an optimal circumscribing ellipsoid around this convex body defined by your hints. But and this is known as, in the literature, as the Lohner-John ellipsoids. But finding this optimal circumscribing ellipsoid, especially for arbitrary convex bodies, is known to be NP hard. So that's kind of a problem. But it turns out for specific geometries, there's closed form expressions that are known, and that's sort of the foundation for the ellipsoid method in linear programming. Like ellipsoid half space and ellipsoid hyperplane intersections in particular have exact sort of really nice, efficiently computable closed form expressions. And so we just apply these iteratively, like you would, for example, in the ellipsoid method itself. And so, as I said, perfect hints are sort of remodeled as ellipsoid hyperplane intersections instead of the conditional Gaussian distribution of this intersection. And in 2 dimensions, it turns out, when you intersect an ellipsoid and a hyperplane, it's just another ellipsoid. So when you do this, you just get a line segment. That's just illustrative as an example. And when we perform some experiments to validate sort of this method for integrating hints, the prior predictions are in blue, and our predictions using this new hint method are in black here. It's kind of hard to see, but we end up with a slightly more accurate, again, due to some of the guarantees here. We end up with slightly more accurate estimates as the number of hints increases. And it's actually quite nice using these geometric hints because there's some quantities in the ellipsoid method and the update methods. And there's the quantity alpha, and this is for both sort of the inequality hints and the perfect hints. I'm going to illustrate this for perfect hints. The hardness of the remaining hardness, so the amount of the effectiveness of your hint is actually governed solely by this alpha parameter. And I'm not going to exactly define how that parameter is calculated, but you can look in the paper. And for alpha between -1 and 1, it says that your hyperplane that is defined by your hint intersects your ellipsoid. The closer that the absolute value of alpha is to 1, the closer you are to being tangent with the ellipsoid, and so the smaller the remaining search space is. And so that's kind of the basic idea behind the geometric hints, and I'm going to talk a little bit about some applications. In particular, decryption failures, I feel like is a really important application here because decryption failures directly map to inequality hints. And in particular, as I said, it's sort of this ellipsoid half space intersection. The prior work had to approximate this inequality, and you assume sort of that after that the distribution of the secret given this decryption failure was a spherical Gaussian in a particular direction of the, and it isn't, that's not exactly accurate. It works quite well for doing hardness estimation, but when you try and use this for attacks, as you'll see in a second, it doesn't quite work the same way you want. And so we experimented using some toy photochem parameter sets so that we tuned it down so we had a high enough decryption failure rate that we could actually generate honest failures. And we tested 50 independent keys, and sort of the averages of all these results are shown here. So on the left graph here, you're looking at sort of this ellipsoid norm, so of the secret. So this is like how far inside or outside of the ellipsoid your secret is. So if you look at in this graph in the red, you're using, this is for the prior method. And as you integrate more and more hints, the secret falls further and further outside your ellipsoid, your search space. And so that results in a much widening gulf in the actual estimated hardness and the experimental hardness. But for our method, again, because we're sort of doing a worst case sort of estimation where we're saying we're guaranteeing that your secret, if it is already inside the ellipsoid, will remain there, we end up with sort of more modest sort of estimations, but the experiments match much more closely. And I really want to impress upon this. This is the main reason why we're trying to get this work to, that we make this work. And you can, we extended this to look at some full-size decryption failures, though this was only an estimation, right? You can't run, actually get decryption failures from an attack or for full-size instances, but we simulated failures from our prior work that use the fault injection to artificially raise the failure rate. Again, I'm not going to really. So the main sort of point here is that the final estimation that you would get from using the prior method is around 307 beta when you're integrating 4,000 ciphertexts. If you take that same corpus of 4,000 failing ciphertexts, we only need this many of them to get around a 10 to 20 beta reduction in hardness as well. There's some optimization methods. We're using this alpha parameter sort of to guide what hints will be more effective to integrate. There's a lot of redundant information there. And so you only need this many, and so it can be more computationally efficient, which is quite nice. And in fact, because of the way this alpha parameter works and talks about how separating hyperplane interferes with your ellipsoid, you can use it to predict hint effectiveness. And so the smaller your alpha is, the higher your chance of, like if you compute this alpha parameter on like an incoming ciphertext before you know whether or not it's a failing or not failing ciphertext, you can, if the alpha is smaller, you actually end up having a higher chance of failure. Though it's kind of opposite of how effective it will be as a hint, because there's this tension between having a low probability event giving you more information. But we experimented with trying to look at this, and we generated a corpus of these of 100,000 ciphertexts, and this 100,000 ciphertexts contained 34 failures under sort of this prior model with the failure boosted, the fault injected failures. And then after you actually integrate all 34, you can see that the distribution of alpha on the remaining 999,000 ciphertexts changes. And in particular, in that bar there, they're pretty much completely unlikely to fail. Most of the failures happen in this bar here. And so finding all 34 failures only required 40,000 queries versus almost a full 100,000 for when you're just doing a linear scan. So there's some geometric analog to failure boosting techniques from Dambras et al, and it's quite nice. I would see the paper for more details. And finally, when we're talking about combined hints, these are modeled as ellipsoid intersections. They're a bit different of a relaxation than these Lohner-John ellipsoids. They come from a technique known as ellipsoid fusion. It's some other notion of an optimal relaxation of constraint methods from control theory. And so you end up constructing such an ellipsoid that circumscribes the region of intersection of two ellipsoids. And as you would expect, as the radius of sort of this second ellipsoid that you're actually intersecting with your first decreases, the hardness also will. And with that said, there's some future work that really needs to be done here. The hint framework is currently limited to the primal attack only on the primal USB attack. And there's sort of throughout my work, and exploring this, there's been this point of like, how do we determine when another algorithm, after you've integrated a bunch of hints, is possibly more efficient? There are times when you actually can gain a ton of decryption failure information, and you can just do sort of a rounding operation and like a scaling and rounding, and you're kind of done. But this estimator might not say that that problem is trivial. So there's some work to be done on figuring out the fatigue points between where you have these different possible algorithms that you can use and which ones are more effective given particular types of information or distributions on hints. There's a lot of work there that I think would need to be done. And then also, another possible thing is that we're using worst case estimates, right? We're using minimally circumscribing ellipsoids. There's this idea that you could say you can use maximally inscribed ellipsoids to sort of give a difference between sort of upper and lower bounds on attack strength. And that could be an interesting thing to look at. There's sort of these inscribed ellipsoids are somehow slightly more complicated to calculate, but there are equations that exist for these geometries known as ellipsoidal slabs, and they can map to sort of ellipsoid half space intersection, but it's not exactly clear how we want to work with these. And also you can incorporate some more techniques from control theory, particularly for combined hints. The techniques that we're using with ellipsoid fusion were invented around 2002, 2003, and there's some state estimation literature improvements that could possibly yield further optimizations, though there's some papers that we read that say that this is actually pretty close to optimal, and it's not exactly clear what we would want to do here. But I think there is some efficiency that we can extract. And I want to say, thank you again, and I'm happy to take any questions.
All right, we have time for maybe one brief question. All right, good. So with that, let's thank all the speakers from the session. And from all of crypto while we're at it. Yeah, safe travels home, everybody, and we'll see you next year. Thanks so much.